In today's video, we'll look into the memory. For a high-end ARM microprocessor, there are basically few different type of memory. Similar to the one we have in our processors, you have the lower levels of the storage, or normally we call it the ROM. So the ROM is where all your data is stored, and the data will remain even though you cut off the power. Somewhere above the storage, we have our main memory, or normally we call it the RAM. The RAM is slightly faster than ROM, so when your system boot up, it will fetch the data from the ROM to the RAM, which is faster for the processor to access. And the third type of memory that we have in the computer system, beside RAM and ROM, is a cache memory. And cache memory is a very luxurious memory that we have inside a CPU or processors, and the speed is very fast because cache is actually built inside the processor itself. And we don't have a lot of cache in a typical processors. Intel processor, for example, you only have a few megabytes of cache that are available inside the processor. When it comes to the ARM processors, the size may be just up to a few kilobytes, and the cache is actually only available for a high-end ARM processor, for example the Cortex-A. The RAM and the ROM is the external chip that connected physically to the processor using a bus, unlike the cache which is built inside the processor core itself. For 32-bit ARM processors, we have a 32-bit address bus. With the 32-bit address bus we could have up to 4 GB of address location, where each of the unique address are representing one single byte. When you sum up all the address that you have, start from 00000000 up to FFFFFFF, you will have total of 4 GB of space. Of course, you can't put all the 4 GB of RAM or ROM into this address, because as what we have covered previously, all the 4 GB of address location are shared among different devices. For example, the RAM, the ROM, and for ARM processors, some of the address was used for the memory map I/O. For example, if you like to connect a ROM chip to the ARM processors, basically this is the range that you are given, start from 80000000 up to BFFFFFF. A typical memory chip, for example, will have two buses connected to the processors. So the first one is the data bus, and the second one is the address bus. Depends on the size of the memory chip. The number of address bus is determined by the size of the memory itself. For example, for a 1 MB of memory chips, there are 20 of address line that are actually grouped into the address bus. If you can calculate 2 power of 20, where 20 is the number of address bus for the memory chip, so you will end up with the result of, basically you will get roughly 1 million of memory location, where each location is 1 byte. If we divide this value with 1024, so you will end up with 1024 kilobyte, and 1024 kilobytes is equals to 1 megabyte. If you have an address bus with 20 numbers of address line, we can basically expect that these memory chips contain 1 megabyte of memory space. When we convert this decimal number into hexadecimals, this equivalent to 1000000 in hexadecimal. So in other words, 100,000 in hexadecimals is equivalent to 1 megabyte. This is the total number of bytes can be allocated inside the memory of the processor. So of course the address is not start with 0. In this case, for example, if you are talking about ROM, the address is start with 8000 and 0000. And your memory will be allocated with a unique address. Start from this value up to 100,000 in hexadecimals. Then the last address will end up to be 0x. However, since we start with the value 0 as the first address, the last address would have to minus 1, which end up to be 0x800f, ff. If we actually connect a 1 megabyte of ROM to this memory map where the address starts from 8000000, the last address for this 1 megabyte of ROM will be 800f, ff. And in some cases, we might have more than one memory chips. So for example, in this case, if we're going to connect two 1 megabyte of ROM to these processors, as what we have just calculated just now, for the first memory chip, the address start with 8000000, and the last address for the first memory chip is 800f, ff. So the second memory chip that we're going to connect to these processors, the address for the second chip will start with 80100000, and the last address for this memory chip will be 80100000 plus 100,000 in hexadecimal. Since both of the chip it has the same size, which is 1 megabyte, and the hexadecimal as what we converted just now is 100,000 hexadecimals. And lastly, we have to minus 1, similar to our scenario above, because the address starts with 0. When we want to calculate what is the last address, we have to reduce the value by 1. And lastly, the last address for the second memory chip would be 0x, 01f, f. When we compare the RAM and the cache, basically cache has a slightly different architecture than the RAM, where the cache is used to store the data or instruction that waiting to be used by the processors in a faster speed. So what the cache does is it holds the common data that the processor might need it over and over again. And since the cache memory has a very high speed compared to the RAM, more often the processor is going to use the data, the faster you're going to get it from the cache. If you compare to the RAM, where your processor will need to fetch everything from the RAM over and over again, the speed will reduce a lot based on the bottleneck of the RAM. So that is a controller inside the cache memory that try to figure out which of the data that the processor would need a lot, so that it will keep the data in the cache, so that the processor will be able to grab whatever data easily from the cache. In the normal operation, when the CPU try to get a data, it will first try to search the availability of the data in the cache memory, and when the data is not available in the cache, only then the processor will try to load it from the RAM. Cache become a very important element because it will make your processor to run faster, although a computer could run without a cache memory for a lower end processors. But in that case, the processor will be running slower compared to the one with a cache memory, because every time the processor load an instruction or data, it will have to go through the RAM or the ROM, which is much slower speed compared to the cache. And there are different levels of cache memory. The first one is called the level 1 cache, or sometimes we call it the primary cache. Level 1 cache is located inside the processor itself. It runs almost the same speed as the processors does. And some processor might have a level 2 cache. And level 2 cache is actually outside of the CPU core, and it will run slightly slower than the level 1 cache, although it is still very fast compared to the external RAM or ROM. And normally level 2 cache will have slightly larger memory space compared to level 1 cache, because level 1 cache is actually built together inside the CPU core, and level 2 is outside of the CPU core, which allow us to have a larger memory space. When a processor tries to search for instruction or data, it will first go to the level 1 cache. The processor could not find what he's looking for, then he will go to the level 2 cache. Therefore, the algorithm in the cache memory is so important, so that the processor will get most of the data and instruction from the level 1 cache or level 2 cache instead of going to the memory, because the speed will be greatly reduced when the process need to look for the data further down to the memory architecture. For example, in this case, we have a processor on the top. We have the level 1 cache memory, we have a level 2 cache memory, and lastly, we have the main memory, which is the RAM or the ROM. For example, the access time for level 1 cache is only 1 nanosecond, and for level 2 cache is 10 nanoseconds. And lastly, when it need to go to the main memory, it would take about 100 nanoseconds in order to get the data. The performance of the cache memory is evaluated by calculating the miss rate or the hit rate of a cache memory. So the hit rate is how high is the chance the processor, when it requires a data or instruction, can be found in the cache memory. And the miss rate is the 100 minus the hit rate. So in this case, the level 1 cache has a miss rate of 25%, or we could say that the hit rate is basically 75%. Or in other words, 75% of the time when the processor tries to search the data in the cache level 1 cache memory, 75% of the time the data are available from there. And then for the level 2 cache, the hit rate is 70%. Then we could calculate the miss rate for the level 2 cache is 30%. And lastly, for the memory, of course, the hit rate is 100%, because as definitely the data your processor need, if it is not in the level 1 cache, or if it is not in the level 2 cache, definitely it will be available in the main memory. So with this performance, we could basically calculate what would be the average time for a processor to get a data from all this memory based on the performance, the hit rate for level 1 and level 2 cache. So for example, for level 1 cache, the time that is required to get a data from level 1 cache would be 1 nanosecond, which is the access time of the L1 cache, multiplied by 75% of the hit rate. So the time is 0.75 nanosecond. And because of the miss rate, 25% of the time the data is not available in the level 1 cache. And then that's the time that the processor will have to go to the level 2 cache to look for the data it needs. And when it reaches to the level 2, it already spent 1 nanosecond at level 1 cache, and processor have to spend another 10 nanoseconds to look for the data in level 2 cache. And the total time that the processor could find a data in the level 2 cache would be 1 nanosecond plus the 10 nanoseconds, which is the access time required by the level 2 cache, and multiply by the hit rate of level 2 cache, which is 70%, and then multiply with 25%, which is the miss rate from level 1 cache, and the value will be 1.9. When both level 1 and level 2 cache doesn't have the data that the processor required, then the last result will be go to the main memory, and the time required to access to get a data from the main memory will be 1 nanosecond, which is the time spent to search in the level 1 cache, plus a 10 nanosecond, where is the access time that is spent to search for the data in level 2 cache. And lastly is the amount of time that it requires to look for the data in main memory, which is 100 nanoseconds. And of course the hit rate is 100%, and not all the data the processor will require to get it from the memory. So we have to multiply with the miss rate, where the data is not available in level 1 cache, which is 25%. Also the miss rate of level 2 cache. And finally the value will be. So with this system that we have, we could calculate the average time when a processor requires data. The probability of the data available level 1 cache or level 2 cache memory is calculated based on the hit rate and the miss rate. So the average time for this system will be 0.75 nanosecond from the time where it can get the data immediately from the level 1 cache, plus the time when the data can be retrieved from the level 2 cache. And lastly, when both data is not available in the cache, where the processor will have to go and fetch it in the main memory, where the time will be 8.325 nanosecond. Basically, the average time a processor could get a data from either level 1, level 2 or the memory, at the average time will be 11 nanosecond. So as you could see, as long as you have a high hit rate at the level 1 cache or level 2 cache, the access time will be significantly reduced compared to the scenario where the miss rate for both of the cache memory is very high, and when the processor need to spend most of the time in the memory to get whatever he needs, the average time will increase significantly. So this concludes the video today, and I'll see you in the next class.